Bom dia, pessoal. Saudações espaciais a todos. Bem-vindos aí a mais uma edição do seminário do grupo acadêmico, seminário acadêmico do grupo de pesquisa E2MoC, né, aqui do ITA. Primeiramente, já agradeço aí a participação de vocês aqui nessa manhã de sexta-feira e também agradeço já ao nosso ilustre convidado de hoje, o professor Jandro Abot. Então, uma imensa gratidão, professor, por ter disponibilizado seu tempo para estar vindo aqui apresentar um pouquinho do trabalho do senhor e do grupo de pesquisa na Universidade Católica aqui para a gente. Gostaria de apresentar, antes da gente dar início, aqui rapidamente o grupo de pesquisa, o nosso grupo de pesquisa para aqueles que não são do grupo, né, para poder conhecer um pouquinho do nosso trabalho. Eu vou compartilhar aqui um slide de uma apresentação que eu tenho. Espero que vocês estejam vendo aí. Bom, nosso grupo, né, chamado E2MoC, são aí um acrônimo, né, para as nossas linhas de pesquisa, que é Engenharia de Sistemas Espaciais, Mecânica Orbital e Controle. Né, nós somos aí um grupo que atua dentro do Centro Espacial ITA, né, que é uma divisão ali, um laboratório do ITA, né, responsável para a gente construir. A gente trabalha com pequenos satélites, né, nanosatélites, microsatélites, e o nosso grupo utiliza, né, como pano de fundo aí os projetos dos satélites, os problemas que aparecem nos projetos, né? Então é legal porque os trabalhos geralmente são baseados, né, em problemas reais ali de projetos. Então os alunos têm além de trabalhar na parte da pesquisa, né, acadêmica, também tem essa experiência, né, de conviver ali com um projeto real de um satélite, tá? Então, tanto sendo na parte de engenharia de sistemas espaciais, na parte de astrodinâmica, né, mecânica orbital, e também na parte de sistemas de controle, né, que envolve tanto a parte de guiamento, navegação, filtros e também controles, né, modelos de atuadores, sensores. Então, nos últimos anos, a gente tivemos diversos trabalhos bastante interessantes, publicações em revistas de alto nível, periódicos, apresentações de trabalho em congressos internacionais, então, vários trabalhos muito interessantes. E vocês podem, né, consultar esses trabalhos, acabei não colocando, aqui está faltando slide aqui, acho que está desatualizado, mas nós temos o nosso site, que é e2moc.ita.br, tá? Então, no nosso site tem todas as publicações lá do grupo, né, tem todas as nossas linhas, as pessoas que trabalham no grupo, né, nós também temos a nossa página aí no LinkedIn, no Instagram, então deixo o convite para vocês. Nós fazemos seminários acadêmicos todas as semanas, né, praticamente todas as sextas, porém nem todos são abertos, às vezes a gente tem os trabalhos internos do grupo para discussão, alguns seminários nós temos aí os convidados, né, como esse, daí a gente disponibiliza, né, depois o link da gravação, o nosso canal no YouTube, também para as pessoas que não assistiram poderem assistir esse trabalho aqui, tá bom? Então, agradeço aí novamente a todos. Então, a nossa dinâmica, né, aqui do seminário vai ser a seguinte, o professor Jandro vai fazer a apresentação, né, e daí depois da apresentação eu estaria abrindo aqui para as perguntas, comentários que vocês tenham. Vocês podem optar pelo escrever no chat. A gente gostaria que desse preferência para abrir o microfone, abrir a câmera, se possível, né? Interagir com a gente e colocar ali, fazer os comentários, fazer as perguntas que tem. O professor Rando vai ter a maior satisfação aqui de estar respondendo a todos, tá? Aí eu peço que vocês também mantenham os microfones fechados, tá? Para evitar ruído, qualquer tipo de problema. Sandro, novamente, muito obrigado mesmo por estar aqui. Eu sei como é corrida a vida, como todas as ocupações, mesmo assim, achou um tempinho para vir apresentar o trabalho aqui para a gente. Então, por favor, quando quiser começar, só compartilhar aí sua tela, fica à vontade.
Tá. Ok, muito obrigado, Willer, que é o meu colega, que está na aula aqui muito pertinho da minha oficina, que este ano aqui o Willer está conosco na Católica. Bom dia para todos, pessoal, um prazer estar com vocês. Eu sou Jandro, professor Abot, aqui na Universidade Católica da PUC do Washington, tá? Eu sou uruguaio, sou um cara uruguaio, eu vim para Estados Unidos em 1996, tá? Eu sou engenheiro estrutural, eu peguei engenharia, eu fiz mestrado e doutorado na mecânica aplicada, tá? Eu trabalhei muito com os materiais compósitos, tá? Em 2009 era professor na Cincinnati, eu estudei na Northwestern, tá? No Chicago. E depois foi professor na Universidade do Cincinnati, em Ohio, no estado de Ohio, aqui nos Estados Unidos. E nós começamos a trabalhar com nanotubos de carbono, tá? 2009. E depois começamos a trabalhar com fibras, tá? De nanotubos de carbono. Eu adoro essa área de pesquisa, que é basicamente desenvolver as fibras de nanotubos de carbono como sensores, integrados em materiais compósitos, em materiais poliméricos, metais. E a ideia é sensar a estrutura, sensar contra daño, medir a deformação unitária, medir temperatura, detectar distintas sustancias. É uma área que está crescendo. Nós temos agora um projeto com a Petrobras em Brasil, tá? Eles querem monitorar quando você repara as tuberias, tem que monitorar o reparo, ver se está tudo certo. Tá? Temos um projeto que é bastante grande, por 2 anos, eu acho que são 3 milhões de reais. Tá? Estive na ITA, é um projeto com o professor Domingos Rade, não sei se vocês conhecem. Ele é professor da engenharia mecânica ali na ITA, tá? Eu estive ali no dezembro, janeiro, vou voltar agora em junho. Então, se você quer falar com ele um pouquinho, eu vou estar ali no próximo mês. Eu tenho uma conferência na França, da nanotubos de carbono, depois volto para Brasil. E depois vou para o Uruguai a ver os meus pais. Ok. Então, eu vou falar um pouquinho aqui, vou pôr na apresentação. Eu vou falar em inglês, tá? Porque os slides estão em inglês. Estou acostumado a falar assim as apresentações técnicas em inglês. Mas se você tem alguma pergunta, eu posso falar em português e eu posso fazer switch de inglês a português, tá? Tá, eu vou apresentar aqui, vou pôr na apresentação. Eu tenho 40 slides, eu vou tentar assim 40, 45 minutos, tá? Ok,
Enquanto isso, Jandro, você coloca aí, eu acabei esquecendo de me apresentar para o pessoal que, que não é daqui. Eu sou o professor Willer, né? Eu sou do Departamento de Sistemas Aeroespaciais, do ITA, também faço parte do Centro Espacial ITA. E eu estou aqui na Universidade Católica Americana como pesquisador, professor visitante, né? E também fazendo pesquisa com o pessoal da NASA, de Goddard, na área de controle, dinâmica e controle de informações em voo. Então, essa é a minha introdução.
O Willer é um muito bom colega, tá? Ele está sempre aqui na oficina. Ele trabalha mais que muitos de meus colegas aqui na PUC. Tá tudo bom, ok.
Obrigado.
Eu vou pôr aqui, vou colocar a apresentação. Tá. Tá. O título é Integrated Sensing Using Carbon Nanotube Fibers in No Space Applications. Eu queria falar com vocês assim na parte técnica, mas também falar um pouquinho das aplicações, tá? Aplicações eu acho que são muito relevantes para a parte aeroespacial, tá? Pode ser vou falar em inglês, the aero part and the space part as well. The space portion, we haven't done a lot of work yet, but I think there's a lot of potential. The collaboration with Wheeler and perhaps some of you in the future may yield some progress in that. We are talking about different ideas for satellites, monitoring the boom vibrations and things like that, this fiber can play a very, very important role. So, like I said, my pleasure to be with you guys, and I'm going to, tell you about the work that we've been working, like I said, since 2009. So it's been, 14, 15 years. So I really, honestly speaking, I don't want to do any other research that doesn't involve the CNT fiber. So that's really my passion. And I have 7 doctoral students right now in my team. And, we are working on that. And I have many students who already graduated with us. So you can see in the screen here, I cannot see your faces, but I can certainly see my slides here. So the idea is to use this fiber, which is a 30 micron, okay? I don't know if you have an idea how much is 30 micron. Our hair guys, is about 100 microns in diameter. Okay, so 30 microns is thinner than our hair. That's a fiber that we use. This fiber can be basically weaving a structure. It could be as part of the structure in a plane. These are what you see in the screen. These are concepts. They are not real applications yet. Okay, so our goal is to develop the technology to have those sensors implemented, right, integrated in structures, aerospace structures, naval structures, and basically be able to measure deformation, detect damage, measure temperature throughout the structure. What are the advantages? You have sensors all over, okay? So we call that distributed sensing. Integrated sensing means that you have the sensors inside the structure. So you could also put them outside, but the idea is such a small fiber, okay, that is very easily integratable, okay, in a structure. It could be a composite, it could be a polymer, it could be a metal, it could be a ceramic as well, okay? And they are so light that they won't add much weight to the structure. So that's a really nice feature as well. And you can actually collect the data in real time. That's the beauty of that fiber as well. So it has a lot of advantages compared to other structural health monitoring systems that are out there. I'm not sure if you're familiar with those. There's ultrasound, there's many wave propagation techniques. There's so many techniques out there, but the equipment that is required is quite complex. You need to know what the baseline looks like. In this case, sensing is it's a lot simpler. So this is kind of big picture description of the work. Okay, just to kind of we call it like a cartoonish vision of the project. So I put an outline together for you just to see the things I'm going to cover. I'm going to cover a little bit of each topic. I don't want to bore you. I kind of want to give you an overview of all the research that we've been working on. If you're interested in a specific topic, we can chat. We publish a lot of papers in each of those subjects, and we can chat about each of those if you're interested in any of those. So I give you a vision of that work. Then we'll talk about the CNTR material just for you to kind of know where the material is coming from and what is the idea. There are actually many people. There are some people in Brazil working with carbon nanotube fibers. I think there are some people at USP. There are some people in Minas Gerais. I'm going to go to this conference in France. I think there are a couple of people who are from Brazil working on that area as well. So there are people all over the world, working on carbon nanotubes probably for the last 20 years or so. So then I switch gears and talk about the piezo impedance, which is basically the sensing mechanism for these sensors. And then we'll talk about the different sensing concepts. And then I'll talk a little bit about the fiber, the mechanical, the electrical response of the fiber. And then I go and basically mention about the things that we can do with the fiber. What kind of sensing techniques we can use. So we can do damage detection, strain sensing, temperature measurement, measure dynamic signals, and then we can have a few, I'll mention about a few other things. We can put this stuff in 3D printed, put it underwater. We can do energy storage. We can do wearables to, measure things within the body. So there are quite a few things that we can actually do. So not to bore you too much with the materials portions, okay? But basically the CNT fiber, okay? Imagine you have a single layer of carbon atoms. That's a graphene layer, okay? Like a single layer of graphite, okay? It's called graphene. Imagine you fold that graphene layer and you form a nanotube, like a cylinder, okay? So that's a single nanotube. It could be one wall or it could have several walls. That's a single wall or multi-wall. Imagine you grow those nanotubes and then you spin them and you form a fiber. These nanotubes, these carbon nanotubes have a very high set of mechanical properties, electrical properties, and thermal properties. It's the best material in the world, okay? Highest stiffness, like a 1 terapascal, highest thermal conductivity, highest electrical conductivity among all materials. Because the electrons basically, there's something called ballistic conduction. The electrons basically flow very nicely in those nanotubes. When you put them into a fiber, that's a different story, okay? The fiber will not, because you have a lot of porosity, you have a lot of defects, so conductivity is not as great. But we focus on the piezoresistivity portion of that response. So like I mentioned to you guys when I mentioned my story about Cincinnati. So my colleagues in Cincinnati, they were making a furnace, building a furnace to grow the nanotubes. So you can see here on the left, these are the nanotubes. Imagine they're like trees that grow in a forest. Okay, so you grow those nanotubes. I'm not sure if you can see my mouse. Can you see my mouse, Wheeler?
Yes, we can, Jandro.
Oh, okay, great. So you basically grow those nanotubes in an array or forest, and then you basically start pulling them. And this is so nice, so easy to do. Once you start pulling one nanotube, because of Van der Waals forces, right? These are atomic forces, right? Intermolecular forces. The nanotubes actually get together. Okay, it's not like covalent bonding. They are, weaker bonds, right? But you basically get to form a fiber. So what you see here on the right, that's a fiber. Okay, that's about 30 micron in diameter. So when you look at that, fiber, there are many thousands of nanotubes, right? So if you look at the cross section, you will see all the tips of those nanotubes. The nanotubes tend to be like 400, 500 microns in height. Okay, so that will be the height of the array, and then you start spinning them and you form the fiber. They could be shorter, they could be taller. This material actually I don't produce myself here. I buy it from my colleagues in Cincinnati. They have a lab. They have like $1 million type of equipment to fabricate the nanotubes. You need the proper recipes to fabricate that. It's not it's not impossible. This the technology is very well known around the world, but you need the proper devices, the proper techniques, the proper know-how. So I don't want to do that myself. I just go ahead and buy it and focus on the sensing portion. Um, so basically what you see here in figure D, image D, that's basically what I buy. Okay, now for you to have an idea, each meter of the nanotube fiber is about $100. Okay, so 10 meters, anytime I buy a spool, 10 meters, that's $1,000. So it's not the cheapest material in the world. Okay, just for you to have an idea how much it costs. You can actually have a single fiber. You can actually have several fibers together. Okay, you can do 2, 3, 4. Okay, and you can have thicker fibers as well. The fiber that we work is about 30 microns in diameter, but you could have a fiber which is maybe 100 microns. I have a student working on energy storage, so he needs about 100 micron fiber. So my colleagues can fabricate that fiber as well. So you would say, okay, why nanotubes? Why work with that? So if we have copper, if we have aluminum, well, the idea is that you have a very light material, so very stiff, very conductive, both thermally and electrically. Okay, but it's also super light. I mean, it's a very, very light material. It has a lot of porosity as well. So if you compare specific conductivity and specific, thermal conductivity or specific electrical conductivity, compared to copper and aluminum, CNT fibers will beat them. CNTs will be better, but remember, CNTs we're talking about nanometer level. I didn't mention diameter is about 9 to 12 nanometer. That's impossible to handle. We are engineers. We are not, we are not physicists or chemists working a lab. We want to make products. We want to make sensors. We want to use them for real life applications. Okay, so we need to be able to work with something which is more tangible. So something in the micro scale, that's doable. Something in the nano level, very hard to handle. Okay, so CNT fibers are a lot better than copper, and including for cables. I'm not working on that, but there are some people in the UK and other places trying to develop CNT YAN cables to transmit electricity. It's actually better than copper. We can talk about that later. I'm not working on that, but that's a very interesting area as well. So what is the physical mechanism behind sensing using carbon nanotube fibers? Well, it is something called piezoimpedance. Okay, so I'm not sure if you can see my hands here, but imagine you have a fiber, right? Imagine this as a CNT fiber. Okay, so if I pull the fiber, right? If I measure the electrical resistance, I can use 2 probe or 4 probe. The electrical resistance will change. Okay, so I can actually correlate the change in electrical resistance versus the strain. Ok? A deformação unitária, tá? Então, sorry, I switched to English. Okay, so if you measure the electrical resistance and correlated with the strain, you have a piezoresistive behavior, okay? These fibers are mostly piezoresistive type of sensors. But you see, I call it piezoimpedance. What's the difference between resistance and impedance? Well, the impedance includes an imaginary part, okay? That's what you see here, okay? This guy here is called the reactance, okay? The reactance has two components, the inductance and the capacitance, okay? And that's something, that's omega, that's your circular frequency, right? So this is depending on if you do DC current, you only care about the resistance, right? But if you have an alternate current, right, we can actually vary the frequency, then you have a contribution from the reactance. Now, I have a student, he's actually studying this piezoimpedance behavior going all the way to 3 gigahertz. If you go to higher frequencies, the material tends to be more capacitive, okay? And we'll talk about that later. We don't know much about it. We are the first working on that. So my students, he's trying, working on this area. So what is the idea? The idea is that I want to integrate this fiber in a material, okay, in a structure. It could be a plane, it could be a satellite in the future, okay? And I want to measure the resistance. If I'm able to measure the resistance in that fiber, I'm able to correlate it with the amount of deformation in the material. And we will do the same thing with temperature and some other things later on. So that's the basic idea. Why does electrical resistance changes? Because once you deform the material, right, the carbon atoms, they're getting further apart. So that's something called intrinsic resistance, right? But there's also something called the contact resistance, right? And there's something called the tunneling resistance. So all of those type of resistances contribute, okay, to the changing resistance of that fiber, okay? This is all not necessarily quantum mechanics, but once you go to the lower scale, lower level, like nano level and below that, then the laws of physics, or let's say classical Newtonian mechanics physics, kind of break apart, okay? So you need to rely on quantum mechanics and other areas as well to be able to understand that response. And certainly capacitance and inductance, like I mentioned before, they also play a role as well, especially when you coil it, okay? Imagine you have the fiber and you twist it a lot, okay? The inductance tends to change. And because the fiber has a lot of porosity, sorry, let me go back, right? If you look at the fiber there, okay, you see it looks like a solid material. It's not. It has a lot of porosity. It has a lot of air. That means that you have a lot of capacitors because you have a conductive fiber, another conductive fiber, or a bundle, okay, a group of fibers, a group of nanotubes, right? And then you have air in between. That's a dielectric material. So you have a conductor, and air in the middle. That's capacitor. That's a capacitor. So you have a lot of capacitor there, a lot of capacitors in there. That gives you room to store energy as well. We'll talk about that later. Anyway, so the same idea happens with temperature, okay? There are different mechanisms, okay? The most common ones are called variable range hopping, okay? And FIT, fluctuation induced tunneling, okay? So those mechanisms control the flow of the electrons in the material once you increase the temperature. Once you subject the material to a specific or to change to a different type of once you change the temperature in the material, okay? So these are exponential type of relationships, and variable range hopping means that this beta here, okay, can actually vary, right? And take different values depending on this d value. It can go to the fourth, okay? That's the most equation. When d is equal to 3, this goes to 4, right? And then we call that the most equation. I don't want to bore you with all the physics stuff. I don't do physics. Like I said, I'm an engineer. Okay, we want to develop the sensors, but we certainly need to understand what's happening at those from a more physical standpoint. So I want to show you another cartoon here, another kind of big pictures, slide, just for you to see what we are doing and what's the idea. Like I said, I'm trained as an engineer, but sometimes you really need to do a lot of physics, a lot of material science, right, to be able to develop that sensor. So everything starts, let me move this a little bit to the side here. So everything starts with the fabrication of the nanotubes, okay? That's a process called CVD, chemical vapor deposition. You grow those nanotubes, like I mentioned initially. You form like an array or a forest, okay? And then you start spinning, you form the fiber. Once you have the fiber, okay, you integrate it in a material. It could be a polymer, it could be a composite. That's what we do most of the time, okay? And then you need to form a circuit. I mentioned to you that we need to measure the resistance, right? So I need to form a circuit, okay? So that circuit, okay, requires forming electrodes, and I need to be able to have access to those electrodes, okay, for me to be able to measure either the electrical resistance or the electrical impedance, okay? You can have actually 50 sensors, okay? So you form a sensor network. You can have 3, you can have 2, you can have maybe 1, okay? The more you have, the more sensing you can do in your structure. Of course, the more money you're spending, the more difficult it is that setting. But certainly, the more sensors you have, the more data you can actually get from your system, right? From your sensor system. And then eventually, once you form that sensing network, you need to make sure that you get the data, you need to make sure that you get proper data, you need to validate the results, and eventually you get the dream. The dream, guys, is what we call the self-sensing structure, okay? That's a structure that has built-in sensor. We call it smart structure, ok? Você pode usar assim muitos nomes, tá? Mas a ideia é que, the main idea is that you have a structure that has already embedded sensors. So when you put it into use, right, it has already the sensor you can actually tap into and get a lot of data. And you can do a lot of different measurements. You can measure a lot of different things. So isn't that nice? I think it's pretty nice. So I'm going to mention some of those things here, like damage detection, strain measurement, temperature sensing, motion sensing, detecting chemicals. I'm going to talk also about energy storage. So, okay. So I'm an experimentalist. That means that we do a lot of experimental work in my lab. We do fabrication, we do experimental work. We also do computational work. I had a couple of students, one graduated already, Akbar. He did a lot of computational work. He was coming from a background of computational mechanics, and he wanted to work with me. So I said, okay, fine. So let's work with the CNT fiber. So, and I have another student in Iran. He's also doing computational work. But most of our work is on the experimental side. And imagine you had to work with the fiber, right? The fiber, I don't know if you can see here, but there, that is a fiber. Okay, the fiber is 30 micron diameter type of fiber. It's super slender, super soft. If you apply a force, if you just pull a little bit hard, you break it. If you don't handle it properly, if you just squeeze it, you lose the fiber. You damage the fiber. So we basically had to develop. I'm a mechanical, characterization person by training. So we are, used to, testing polymers and composites and metals, right, ceramics. So the losses, when you put it in a servohydraulic machine, in a mechanical testing system, you're using we typically use losses that can carry 30 kilonewtons, 50 kilonewtons, right? So that will not work for the fiber. So we basically had to purchase new load cells. So you can see there, that's a load cell, can handle maybe 3 I think I forgot what is this one, but maybe 2 newtons or 5 newtons. And then the grips, these are titanium grips, and then you have to develop some kind of fixtures to test the fiber. So you pull, you apply a mechanical load, you measure the resistance. So we do a lot of electromechanical characterization, mechanical, electrical. We also do thermal. We also do electrochemistry as well. So just for you to kind of have an idea of what we are working on, okay? Now the fiber, that's an expression in English. I don't know how to say it in Portuguese, but the expression is a gift that always keeps on giving, or something like that, okay? What that means is that the fiber is a very complex material, has a lot of, from a research standpoint, it has a lot of interest because there are so many parameters that play a role in the piezoresistor response. For example, what do I mean by that? If I make the fiber thicker, the response will be a little bit different, right? If I pull the fiber very fast, the response will be different, okay? If I coat the fiber with a polymer, the response will be different. So I'm not saying that, this is a great thing for sensing. I'm sensing that the fiber has a lot of parameters, okay, that can control your response, the piezoresistor response, or the piezoimpedance response, or the thermoresistor response. So you need to be able to understand, okay, the role play by all of those parameters in that response. And I don't want to bore you with all of those because we have published quite a few papers in the last 10, 15 years. Okay. But I want to show you just a couple, just for you to kind of get the picture of what I'm talking about here. And, and I will tell you a story actually. And this is it's a funny story when I tell it, but it wasn't at the time. It wasn't really funny. So my first student, okay, was a master student. So he was. I show you this setup here. So he was basically testing the fiber. He was actually using 2Pro. I'm not sure if we have any electrical engineers in the audience, but there's a difference between 2Pro and 4Pro measurements. 2Pro means that you have 2 probes, right? And you measure, you pass the current and you measure, right, with one set of probes. But then if you have any contact resistance and you pull, that may affect your results. So a 4Pro measurement is actually better. So my first student, okay, that was a master student. His name was Tarek, very bright guy, very smart guy. So he started measuring the resistance where he was pulling the fiber. So he got a response that looks kind of like this. What you see here, right? I measure relative change in resistance versus strain. Okay, what do you see? The red line there. The red line is coming down, right? What does it mean? It means that when you pull, the resistance decreases. That was not intuitive to us. And you can see here in parentheses the rate. We didn't know. At the time, we just pulling, okay, we got this data. I tried to publish that. I went to Carbon. I'm not sure if I put the journal here. I think, no, it's a different, okay. This is a different journal. But anyway, so we tried to publish in Carbon. They denied the paper. Said, no, somebody else got a positive response. So somebody else had published and they had published a result like this, okay? So you would pull the fiber and the resistance will increase. So it will be, what we call a positive piezoresistor response. But I was sure that the response was negative. We kept on telling the same thing. So anyway, we argued with the editors, went back and forth, we explained, we showed the data, and said, fine. They agree, we published in Carbon. That was in 2014. So that was our first paper on this subject. My student graduated, fine. Then another student came, Jude, another excellent student, physics background, material science background. He goes to the lab, this guy is all day working in the lab, Professor Abot. I'm getting a different response. So he was getting responses like this. And I was, wow, we already published that. I argued so much. We kind of won that battle. We managed to publish the work. And then he says, Professor Abot, I'm really getting these positive responses in the fiber. And I said, well, what's happening? And then we realized that the speed at which we apply the load play a role, right? And we managed to figure out, if you see here the figure on the left, right? Once you increase the strain rate, the response even increases. So this is not unusual in polymers, okay? If you increase the rate at which you apply the load, right? The material becomes stiffer, okay? So that's some kind of what we call the strain rate dependence. So in the case of nanotube fibers, this is not different in the sense that the piezoresistor response will be dependent on the strain rate. Maybe some minutia, a small thing for me to mention, but the point is that the fiber is dependent on the speed at which you test it. And there's so many other parameters like this that play a role. For example, when you form the fiber, the angle of twist that you exert also plays a role in that response. You can see here, typically the fiber that we use has an angle of twist of 30 degrees. By the way, if you don't twist the fiber, when you pull the nanotubes and you form the fiber, if you don't twist them, okay, you basically have no stiffness. The material is like a loose assemblage of nanotubes. So when you twist it, the material becomes a lot more stiffer, a lot easier to handle, right? And the more you twist, the stiffer the material will be. And also the electrical response will be different as well. So we had a study, we actually played with all of those responses. And what we found is that the best response will be at 30 degrees. So both the tenacity is load per unit weight. Sometimes it's better than considering the stress of the material. And the gauge factor, which is the sensitivity, the slope of the delta. If you look at sorry to go back here, but if you look at the slope of this curve, That's what we call the gauge factor. That's the sensitivity. You want a higher sensitivity. It's like any sensor. The more sensitivity is, the better, right? So we found that at 30 degrees, there will be, the maximum sensitivity. So basically, we kept on working with that particular angle. But we know that if we change the angle, the response will be a little bit different. So like I mentioned to you, some of our students did computational work. So we try to explain some of those results through computational means. We actually, it says here to be submitted. No, we are already published in the Journal of Mechanics of Materials journal. So that was published, I think, it was 2021. So we basically try to understand. We did a lot of fun. It's a hierarchical model. The CNT fiber, you have to go to the nanoscale level. You have the nanotubes. Then the nanotubes agglomerate. They form bundles, and then the bundles form the yarn. So it's a hierarchical response, and we basically study each level, and basically we obtain the stress strain response for the nanotube yarn at the end. And then we compare with different experimental results. So this is work that we are continuing. Right now we're focused on the piezoresistor response. So if you guys are interested in learning more about that, I can mention those things a little bit later. Going back to the CNT fiber and what we can do in terms of sensing. Well, the first thing that we actually managed to do was in 2010. We said, okay, I'll tell you another story. I have somebody who's asking. I'm in a presentation right now. So it's a Jandro, what can you do with the fiber? I said, well, I was working with composite materials at the time. You probably know composite materials are used in planes, used in space applications. They're very light, they're very stiff, they're very strong, right? So the only issue with composite materials, okay, one of the drawbacks is that they're laminated materials, right? And when you delaminate, right, if you pull in the transverse direction to the laminate, the materials delaminate, right? And they basically damage, and you don't see the damage, right? So then we said, well, can we use some fibers to stitch the composite, the laminated material, and measure the resistance in that circuit once you form the circuit? And then, well, if there is some kind of damage, right? Imagine the layers start opening up, then the fiber will be pulled. If you pull the fiber, what's going to happen? Piezoresistor response, right? So the electrical resistance will change. So now if you keep on pulling, right? If the laminate keeps on delaminating, right? The layers keep on separating, right? You are pulling more the fiber. Eventually you break the fiber. When you break the fiber, right? The circuit is gone, right? You short circuit the structure, right? The fiber, and the resistance goes to infinity. So then I know that there is damage in the structure, right? And then we can detect damage. So laminated composite materials typically composed of carbon fiber and glass fiber, right? So carbon filaments, just for you to, if you are not familiar, they are 7 microns, right? And you form bundles, typically like a 3,000, 6,000 filaments together in one bundle. So if you put a fiber, a carbon nanotube fiber, 30 microns, it won't do anything. The composite won't even see it there. And it's also friendly in the sense that, a carbon material, is nicely fitted with another carbon material. You probably have to isolate it because they're conductive. But the point is, this is a very friendly material to integrate. And you have already an embedded sensor in the structure. So believe it or not, I mean, you can fly a commercial liner, right? Or you can fly a military plane. They don't have any sensors embedded in the structure. So if something goes wrong with the structure, there's no way for you to know. The planes are certainly tested every certain number of hours. They take it to a hangar. They subject it to ultrasound testing and many other techniques. And you can determine that delamination. But you can do 30 flights and you still don't know that you have damage in the structure. So the idea is for you to be able to put the fiber in the structure and be able to measure that in real time. I think that's the beauty. I'm gonna speed up a little bit because I'm looking at the clock here. So you can integrate that in composite materials. It could be glass materials, it could be carbon, they could be made on what we call prepregs, okay, that have the polymer in there. It could also be dry fabrics. So this can be done in many different ways. And the basic idea is, okay, this graph has a lot of graphs here, a lot of lines, okay? But imagine I plot the load versus time, okay? The blue line, okay, that's the load, okay, over time, okay? So imagine I have a sample, I put this is top view of a sample. All of these lines, these are the nanotube yarns. The dashed line means it's a stitch. These are like a flat, okay? So I have a lot of sensors in there, and I put some delamination there. So I put some damage, apply the load, and the damage will propagate. The damage here will propagate. And once it starts reaching the nanotubes, right, the nanotube yarns, then those circuits start failing, okay? So you know exactly the location of the damage, and you also know when it's happening. This is kind of the rationale for the project that we have with Petrobras right now. So we are trying to use the fiber they had to repair a lot they had to implement a lot of repairs on the pipelines, and they want to have offshore platforms by around, I think it's 2030, and they don't want to have any people there. They want to, or the minimum number of personnel in the platforms. So the more data they can actually get on the structures without having people, the more data you can actually get remotely, right, the better. And these fibers are very easily integratable. They could be done in composite structures, but they could also be integrated in metallic structures as well. So damage detection, we published the first paper in 2010, and we've been working since then. This is a very interesting area as well. Now you will say, well, I mentioned to you the structure is failing, right? But how do you know that that's the case? Well, you can actually use something called X-ray microtomography, right? So it's like, when you go, when something happens to your knee or something, you go to the doctor and they do an MRI, right? Magnetic resonance type of testing. So you can do the same thing with the composite material. And actually you can see where the damage is, you can see the fiber, and you can backtrack and say, oh, the damage was there and the fiber was able to see it. So I had a student, he actually, he did a master's a few years ago, Kevin. And we were doing this testing. This equipment is like I don't know how much is it, but it's a very expensive. I'm not sure if you have it at it. I don't think you have it. These equipments are very expensive type of devices. Anyway, so then we are also integrating the fiber in polymers, okay? This is an epoxy type of resin. It's a transparent material, so you can actually put the fiber in there. And then, if you want to see if the fiber is there, you just pass a current. You have an infrared camera, and you can see if the current is flowing. When you don't see this glowing, that means that the fiber is broken. So that's a very easy, way for you to know if the fiber is continuous or not. So the basic idea is I wanted to measure the strength. So damage detection is easy because I'm looking for a high change in resistance. If the circuit is broken, the resistance will go to infinity. Great. If I want to measure resistance, I need to correlate relative change of resistance versus strength, right? And I need to get the slope. So in real life, how do I do that? Put the fiber, measure the change of resistance, okay? Divide by the gauge factor, and now the strength. So I know how much the material is deforming. If my resistance is high, right, divided by the gauge factor, and I have a strength of 1%, maybe the deformation is too high. So maybe I want to reduce the load, unload it, and if it's too much, maybe I'll replace the part, okay? What you see here, I don't want to bore you too much with the details, but this is a fiber. Once you put the fiber in the polymer, it depends on the polymer, right? But the polymer may enter the fiber, and that changes the properties of the fiber. That's a whole another field, right? But the beauty, and I don't want to bore you with the numbers here, but the beauty is that once you have the fiber in a composite, the sensitivity, that slope, is a little bit higher, okay, than when you have the fiber itself, by like an order of magnitude. I have a student, she's actually working right now in USP. She's actually trying to understand the response of the fiber under compression. So she's working with the atomic force microscope, and Raman and so many different things. This is with the electronics team at USP. Another thing that we did, and actually this is something that I actually started, I was a Fulbright scholar working in USP in 2014 and 2015, and I visited ETA for the first time in 2014. You guys probably were not there at the time. So that was my first visit to ETA in San Jose. So I started working on strain gauges. You probably know about metallic strain gauges. Imagine you want to measure the strain on a sample. You get what is called a metallic foil strain gauge, and you bond it on the surface. You pass a current, right? And you measure the strain, okay? You measure the change in resistance, you multiply by a gauge factor, and you determine the strain. The same idea we try to implement with CNT fibers. And so we did a lot of computational work. That was with Professor Silva, Emilio Silva, and USP. And then we started fabricating with IPT in Sao Paulo, IPT San Jose. They helped us a little bit as well. So these are some of the, imagine you have a sample, right? Instead of using a metallic foil strain gauge that is made of Constantine, I use a strain gauge made of carbon nanotubes. So you can see here in orange, that's a change in resistance curve. That I don't want to go into all the details, but you see that the resistance is not coming all the way down. That has to do with the relaxation of the fiber. There's a lot of things that have to be developed yet, but you can use it for strain sensing as well as an external sensor. I'm going to switch topics and mention something about temperature, and I'm going to kind of pitch it to you. Imagine you want to measure the temperature inside a material. How do you do that? You can use a thermometer, you can use a thermocouple, right? And you put it on the surface, you can measure the temperature. Great. But imagine I have a mouse here. I want to measure the temperature inside the mouse, in the middle of the mouse. How do I do that? So the idea is for us to be able to integrate the fiber. We do it in polymers these days, right? Then we cure the material. So we had to go through a process of, curing. Once you put the fiber, right? Once you put the polymer, right? You have a mold, right? And you pour the polymer in the mold, and you have the fiber, right? There's going to be a curing process for the fiber. And so there's a lot of electrons that get into the fiber, so the electrical resistance will change, then it will come back up. It has to do a lot with the chemistry of the polymer itself. We work mostly with structural polymers, that means epoxies, polyimines. These are the strongest, stiffest polymers, but you can actually use any type of polymer. We use soft polymers as well for different applications. So once you finish the curing, okay, you end up with this value of the resistance, okay? That's my initial resistance, okay? And then I don't have the data I have the data in the paper, but I didn't put it in the presentation. Once you have the sample, you can use cyclic loading, you can do so many different things, right? And you obtain something called the temperature coefficient of resistance. So what is the idea? The idea is that you measure, okay, like we did for the strain. We measure the change in resistance, divided by this coefficient, and determine the temperature. Like you determined the strain before, you can also determine the temperature. All you need to do, okay, going back to the mouse, is have a circuit, get those electrons, measure the change in resistance, and then you get the temperature. So you can actually see here, we haven't published this work. Actually, my student, she was actually getting her degree yesterday here. So she's finishing a paper for sensor and materials. So this is the correlation between the measured and the calculated temperature. So the fitting is excellent, okay? You can do cyclic loading, you can do different steps, okay? And you basically have a thermocouple or a thermistor, okay, embedded in the material. So we want to develop that technology as well. There are a lot of things that have to be studied, certainly the way you fabricate the material. There are issues with the strain rate, issues with the coefficient of thermal expansion. So there are a few things there are a few, what can I say? A few corrections that had to be implemented, okay, for you to be able to get a final temperature. So, but we are working on that as well. We don't have any funded project on that yet, but we are working towards that as well. Another interesting area that we are working on is the dynamic response of the fiber. I mentioned to you when we apply the load, right? That's what we call a quasi-static load. You apply the load, right? But imagine you apply the load in a dynamic fashion, okay? And it could be, with a high frequency as well. Maybe this a little bit, this line is a little bit difficult to see, but maybe you can see it a little bit better. That's the experimental setup here. So imagine I have the sample, put it in a polymeric material, right? I'm putting a shaker, and I shake it, right? You know what a shaker is? You apply a vibration, right? So you need an amplifier, right? You need to, basically get the signal from your computer, amplify the signal, shake the structure, and then I put an accelerometer here. I put a strain gauge, and I have my fiber here. What I want is the dynamic response of the fiber. I measure the strain. This is a dynamic strain gauge. This is, we purchased from a German company called HBM. So it's a very expensive gauge, right? And I measure the strain from that gauge. Measure the resistance. So then I can actually plot the change in resistance versus the strain, like I did for the quasi-static loading, but this is dynamic loading. So let me see if I can show you this graph. So we basically get what we call the frequency response function. So you have an output, you have an input, you take the ratio. That's what we call the frequency response function. So the lines are a little, okay, sorry about that. The lines are a little bit too clear here, but I basically want to correlate the data from the strain gauge and the CNT yarn. So at the end of the day, I can plot relative resistance change versus strain, but I can do it versus frequency. So not just versus strain, but versus frequency, right? And right now we are basically going up to about 1 kilohertz. We are trying to get a new device to go to 10 kilohertz. We are trying to go even higher to 30 kilohertz, but then the amplifier, just the things get a little bit pricey in terms of amplifiers, and the experimental setup a little bit difficult. But the main idea is that we also want to be able to use the fibers to detect all kind of dynamic signals. Okay, that could be in the air, that could be underwater. If there is an explosion, for example, the fiber will be able to hear that. Okay, so the applications are really interested, maybe more on the defense area. I think it has a lot of potential in the fiber direction and in the lateral direction as well. I don't want to get into that because that's a whole another story. But the fiber is very sensitive in the fiber direction, but laterally in the transverse direction, it is super sensitive as well. So imagine you have a fiber and people are talking, the fiber can actually hear that as well. And there will be deformation in the fiber. So that's what Iliana is actually, one of my students working on that right now. Anyway, another area that we're working is, imagine you want to have some kind of vehicle underwater, right? And I want to be able to measure, I want to know how deep is the structure, for example, or how much deformation you have in the structure. Imagine you put the fiber, right, in that structure. This is like a 3D printed structure, okay? It's actually made of, I think this is ABS, okay? Acrylonitrile butadiene styrene. And you put it underwater, you can actually measure the change in resistance, okay? Piezoresistive behavior. You backtrack the strain. It's a thin wall structure, thin wall vessel. Calculate the stress, right? Like a hoop stress. From the hoop stress, you get the pressure. From the pressure, you can get the depth. So there are many things you can actually do with the fiber as well. It's kind of hard to see here, but the fiber is actually embedded in that 3D structure. It's not easy to do. I was actually chatting with another student. He graduated actually with a master's in material science. So he was very busy, but now it's summertime here, so he's gonna continue working on that. So we have a collaboration with a local company here who wants to develop that technology. Another area which is super interesting as well, which is a little bit about my expertise, is in the electrochemistry field. So these fibers have a lot of surface area because you have a lot of filaments and they have a lot of area and they have a lot of porosity. Okay, so they have something that we call fast electron transfer kinetics. So that is very good to detect all sorts of substances. I mean, I'm talking about biological substances, chemical substances. And so we are collaborating with, some other, universities. We have a local university here called American University. They're in Washington, D.C., like us. He's a wonderful colleague. He's a chemistry person. So we do a lot of cyclic voltammetry, okay? What I mean by that is we measure, imagine you have the fiber, you put in a solution, okay? And you measure, you pass a current, okay? And you measure the voltage. You get these graphs, they are called voltammograms, okay? So from these graphs, you can actually get the capacitance, you can get the energy density, you can get power density, okay? And you're based on the shape of that graph, you're going to be able to determine what chemical are you detecting, okay? And what's the concentration of that chemical. Looks like science fiction, but it's really my original thought. Imagine you are in a plane and there's something leaking in the floor. So imagine you have that floor with that fiber in there. So the fiber will be able to see if there's water or any kind of liquid seeping into that floor. You may be able to detect it before you have a big issue. That could be gasoline, it could be benzene, it could be any kind of chemicals. Not every chemical will have the proper electron kinetics for the fiber, but many of them do. So I have another student, she's actually biomedical engineering. So she's actually trying to detect neuropeptides, a lot of neurotransmitters, like serotonin. There are so many other chemicals that can be detected. I mean, my colleague is more interested in the bio applications. I'm more interested in the engineering applications. But we are basically trying to develop sensors that come in kits. So you can actually use it at home to detect many different things. I'm not saying COVID, but I'm saying many things could be detected through these fibers as well. We don't have any prototypes. We're certainly working to that. We built glucose sensors. We didn't quite start that collaboration with the team in Colombia, trying to use it for insulin detection. So many different things. And I kind of want to wrap up with two different things. I think it's already 10:03. So just with two different concepts. One is the energy storage. Like I mentioned to you initially, we have the fiber could actually be made into a supercapacitor because you have a lot of capacitors in there, so you can use it to store energy. So when I mentioned to you, I put this fiber right in a structure, and I want to measure, strain or the measure temperature or detect damage. But how about that if I'm in the middle of nowhere, right? I need a battery. Well, I could also store energy on the fiber itself, and I can use it to measure the sensor. So I have a student, he's actually finishing this summer, working on that. And I will finish with this. Imagine I put the fiber now in a very soft polymer, okay, like EcoFlex. These are like silicon rubber type of materials, right? And I attach it to like a hand, for example, okay? And I can actually get this response, the relative change in resistance, right, versus time. And when you move your hand, okay, or move your fingers, right, there's going to be a specific type of response. So once I see the graphs, I can tell, oh, you're moving your finger, and how much is the finger moving. So let me show you just a video just to kind of wrap up. I think this video is probably from 3 or 4 years ago. This was my student Jude, and this is an undergraduate student. I forgot who he was. So I don't know if you can see here in the graph. That's National Instruments Signal Express software. So based on the graph, you can tell how much you're moving. So this could be used for robots. Okay, if you want to know, for example, the robots is there is a company in Colorado. They approached us. They wanted to do some. We haven't started any work yet, but you may be able to tell if the robot moves his finger or this other finger. Sometimes you may want to be in a sampling line, and you want to make sure that the robot is doing what what he's supposed to do. So you can actually tell, and then you can tell also how much it's moving. So so that's that. I don't, we are trying to develop sensor for many different applications. So we collaborate with people all over the world, mostly Brazil. We have collaborators in Mexico, different parts of the world. So I have a list of here. I mean, it's a long list, and with Dr. Wheeler. He's, advisor of many of you. So we are trying to work on the space area as well, that we haven't done much yet. And like I mentioned to you, we have a project with Petrobras right now, which is a great project. It's a 2-year project. We started in June 2022. And we are discussing about different ideas about, monitoring vibrations. So there are, many interesting things for you to, for us to work in the future. And certainly the space, I'm going to just stop my presentation here. The space sector is one that could certainly benefit from this area. And certainly Embraer, we pitched it to Embraer in the past as well. And I think they will be interested in that as well. I think the aerospace sector has a higher bar, same thing in the space sector. In terms of the sensor, you have, many false positive or problems that, could occur with the sensor. You cannot, risk losing people, based on a sensor. So I think, starting with areas like, infrastructure, oil infrastructure or civil infrastructure, that's a little bit easier. And once you prove the concepts and the sensors, are well developed, then you can move into the, higher performance type of cycle. So thank you for your attention. I stop here. I went a little bit, further, but I'll be glad to answer any questions. And we finished the semester here, so I have all the time in the world to answer your questions and chat with you guys. Like I said, I will be there around mid-June. So maybe I look forward to, chatting with you guys if you're interested in this subject. If not, I hope you learned a few things that are, different from your research. Thank you, Dr. Wheeler Gomes dos Santos.
Thank you so much, Jandro. Obrigado mesmo. Excelente apresentação. Nossa, muito interessante mesmo. Eu mesmo já anotei que tive algumas ideias, a gente pode conversar depois. Mas vamos abrir então para as perguntas. Pessoal, quem tiver pergunta para fazer, professor Jandro, aí fica à vontade. Se quiser fazer em inglês, se quiser fazer em português.
Fala português, não tem problema, tá? Fala português, você vai responder em português.
Professor Jandro, it's Thiago speaking. How are you doing?
Oi, Thiago. Bom dia.
Bom dia. Thank you very much for your great presentation, for the group, E2M, for this amazing opportunity for us. I work at Embraer as a postdoc, and I work at Embraer too. So thank you very much for your time. Professor, only 2 quick questions, please. The first one is regarding the domain. Your yarn, does it work better in AC domain or in DC? And the second question is regarding temperature. When you are measuring some strains or any kind of mechanical analysis that we're doing, you have on your space, when we work with that, we have a lot of difference of temperature. As your sensor work with the resistance variation, how I will know if what we are measuring, it is the temperature or it is the strain? If I have both on the same condition in one part, we have this temperature variation and we have a strain. Both the results are in electrical resistance. How you will know if you are measuring the strain and or the temperature? So these are my 2 questions. So again, guys, thank you very, very much, Professor, and thank you, E2 Group, for this amazing presentation.
Oi, Thiago. Ok, muito obrigado. Sim, eu acho que essas perguntas são muito boas, muito pertinentes aqui no projeto. A primeira, a resposta é a seguinte. O material, a fibra é piezoresistiva, tá? Ou seja, a maioria da mudança, tá? Eu vou falar em inglês agora. The major change, okay, in the sensor, in the CNT fiber sensor, is the resistance. It's electrical resistance under DC current, okay?
Okay.
So we rely on piezo resistance for most of these measurements, both to measure strain or to measure temperature. Okay, having said that, when you go to AC current, right, and you start increasing the frequency, you have another component, right, which is the reactance component, right, which includes the frequency term, the capacitive term, right, the capacitance and the inductance, right? We are actually in the process of getting those results. It's really not a very easy study. I work with several people who have what we call impedance analyzers to measure that impedance response, right? Because we want to basically go from 1 hertz, okay, to 3 gigahertz all the way through, right? What we are finding is that the response, if you go to like 1 megahertz, is basically a resistor. So if the resistance is 1000, right, or let's say the resistance changes 10 ohms, the impedance, the reactance, right, would change like 1 ohm, okay? Now, the capacitance and the inductance will change a little bit more depending on the type of circuit. If you go to like 1 megahertz, the capacitance will change a little bit. There is some work by a couple of French guys. They work on nanotubes themselves, and what they found was that there were some specific frequencies where the material was independent of temperature, independent of humidity. So there's some invariant frequencies that we are basically trying to find for the CNT fiber. So again, summarizing, mostly DC current. We use the fiber mostly under DC current. Once you go to AC currents, can you go to higher frequencies? Yes. Can we use a sensor for higher frequencies? Yes. Will the impedance change a lot? Not really. Would the reactance change a lot? Not really. It will be mostly changing resistance. Now, sorry, I'm going to have a long explanation, but we can chat more, Thiago, if I'm there, if you're interested. There are some people, okay, people at NASA, people in the space sector, they don't want to measure resistance. They want to measure inductance. They want to measure different things. So I think for us to be able to develop a sensor that can measure at higher frequencies has a lot of advantages, okay? In fact, there are some ideas to measure this in a non-contact fashion. So imagine I send a signal, I look at the fiber, okay, look back, okay, and basically what I'm seeing there, I can actually tell you what the resistance is. So I don't know how to do that, but there are some people who know how to do that. They can help us to do that. So that's the answer to your first question. The second question is a very pertinent question as well. If I put a fiber, right? Imagine I go back to the project with Petrobras, right? I have the fiber, right? I put the fiber in a pipeline, right? And it gets, I put the pipeline deforms, right? I certainly measure that deformation. I measure the change in resistance. I can tell that there is a deformation in the fiber, but it gets very hot, right? Let's say from 7 a.m. to noontime, right? The temperature will increase by, let's say, 15 degrees Celsius, right? So you need to be able to have a way to correct the data. So that means that the way it is done with commercial strain gauges, you have like a Wheatstone bridge, and you have a set of gauges, and you have one that is not exposed to the load, it's only exposed to temperature. So you measure the strain due to temperature, and then you subtract it, right, from the strain, from the sensor that is measuring the strain. So you basically correct, and you can tell this is the strain due to temperature, this is a strain due to deformation. So we are going to be doing that. We have a very nice team actually for this project with Petrobras. So we have the Professor Cairo Nascimento, él es profesor en la eléctrica. Él tiene un estudiante que era Juan Ramón. Él está trabajando en esa área también. So yes, you have to correct for the changes in temperature as well. So the way this is typically done is through Wheatstone bridges. So if you have, a Wheatstone bridge is typically 4 sensors, right? So you have one is the variable sensors, but then another one, maybe the sensor which is not subjected to the load, but subjected to the temperature. So then you correlate, you measure both, and you can actually correct that. In terms of the temperature, Thiago, I think you asked me, what was the last part of the question in terms of the correction? You asked me about the temperature range or not?
Well, that's exactly the question, Professor. How, if you have a temperature and strain, how you can know if you are measuring the strain or temperature? But you are using the bridge,
so
the compensating sensor,
you need to
compensating resistor.
Yeah, that's exactly the right word. I didn't use it. Compensation. That's exactly what you need to do to make sure that you correct for the temperature change as well. And this is certainly critical. If you are in the field, right? You are in the ambient air and the temperature changes, you need to be able to tell. And the fiber is super sensitive, so it can actually capture that change in resistance. If you go, if the temperature changes by 10 degrees, you're going to see a meaningful change in the electrical resistance as well.
Exactly, because of I saw your graphs, and because of that I have asked that, because I saw that the arm is very sensitive to temperature.
It is. Thiago, if you are interested, we publish, I think, 2 papers on the, actually, no, we published like 4 or 5 papers on the temperature response. And we are actually trying to come up with a patent as well. So we are not, some things we cannot disclose, at this point, but we are certainly trying to develop this, and certainly the compensation is something that has to be done, and vice versa. Because if I want to measure temperature and the material deforms, right, because of the expansion of the material is the same, I need to compensate for the thermal expansion of the material. So that means that I need to subtract the deformation due to the expansion of the material. So it basically applies both ways. Tiago, excellent questions, and I look forward to chatting with you. By the way, we pitched these ideas to Embraer. That was probably maybe 2016. I think we look forward. We've been chatting with some with the colleagues at ITA. I think we would like to pitch. I think we develop. We have a lot more knowledge, and I think this could be very good. Very good sensor for many specific areas in the aero area for planes, but also for space as well. Tiago, thank you for the question. Muito obrigado pela pergunta. E muito boas perguntas.
Professor, muito obrigado pela explicação excelente. Eu vou te mandar um e-mail aí, a gente vai conversar. De novo, pessoal, do professor do E2, todo o grupo aí. Obrigado pela essa possibilidade de ter uma excelente apresentação. Pensar sempre na gente aí do Brasil aí. Obrigado. Viu?
Coração.
Por ser online, dá para muita gente assistir. Obrigado.
Obrigado, Thiago. Então, o professor Jandro está aberto aí a colaborações, pesquisas, tem interesse. Se a Embraer também tiver, acho que é muito bem-vindo aí. Vocês podem manter contato.
Com certeza. Obrigado.
Obrigado. Tudo bem? Mais alguém? Tem mais alguma pergunta? Comentário? Professor Jandro? Matheus, você tinha levantado a mão? Uma pergunta?
Não, professor. O que eu tinha de dúvida foi basicamente a última pergunta. Então já está tudo certo.
Tá ok. Certo. Oi, Lourenço. Pode falar. Entendi.
Good morning, Professor Jandro. Thank you very much for your presentation. It was really insightful. I have been working during my master's with the modeling of spacecraft with flexible structures. And I see that in this field, we sometimes wonder about really flexible structures, large space structures. And part of the problem sometimes is to identify the deformation of this structure or even the shape that they have. So my question is if you envision this application for to identify the shape of these structures, if it's possible to apply it that way.
Oi, Lorenzo, muito obrigado pela pergunta. Thank you very much for your question. Absolutely, this is, this is great. The fiber, one thing I didn't mention is the following. The fiber, okay, imagine you graph the stress versus strain, tá? A tensão na fibra contra versus a deformação unitária. Você tem uma curva, que é esse strain curve. Tá? A deformação unitária máxima que a fibra pode ter varia com a fabricação da fibra. Tá? Mas esse valor pode ser 10%, aproximadamente. Tá? Entre 10% e 20%. Tá? Então, se você coloca na fibra uma estrutura que é muito flexível. Tá? Quando a estrutura deforma, você tem dois componentes, na parte mais mecânica, vou falar na parte mais mecânica agora, né? Quando você tem uma estrutura muito flexível, tá? Essa deformação da estrutura tem dois componentes. Tem uma componente que é a deformação unitária, strain, tá? Mas você tem também o que nós decimos em inglês a rigid body rotation. Tá? A rigid body rotation is a deformation, is a rotation of the structure, okay? Which does not involve necessarily a unit deformation, a strain in the material. So the strain, when we talk about large strains, you have those two components, right? Your strain plus, okay, to make it simple, the strain is equal to the strain plus omega squared divided by 2. This omega squared, that's not the frequency that we talked about before. Omega in this case is called the rigid body rotation, okay? It's like 1 over radian, okay? So imagine you put the fiber in there, you can actually capture, okay, the strain, right? And you need to figure a way to get that rigid body rotation as well. So the fiber can do a portion of that, and then you need to figure a way to get that rigid body rotation part as well, because the fiber will be integrated in the structure, right? Imagine you have a, let's say, a boom, right? Or some kind of a structure that has a lot of deformation. So you need to figure a way, okay, to get that total deformation. The fiber can measure the strain, because I know the piezoresistor response, right? So if I measure the change in resistance divided by the gauge factor, I get the strain, right? Now the strain will have this other component, which is the rigid body rotation. So we haven't done that work. Can it be done? Yes. You probably need a set of sensors, okay, maybe more than one, to be able to tell the deformation at different locations, right? And be able to correlate that with the displacement length. So I need to think more about it. Lorenzo, is a great question. You probably need to have maybe a model that based on 2 or 3 readings, okay? Because if you have a very long, very large deflection, you probably want to have a sensor, maybe you have a reading here, but you may have another reading here, another reading here. So you need to basically come up with those readings and then backtrack that. We actually did a few years ago some work with the fiber optics, and we were actually I'm trying to remember right now. So the fiber optics were continuous and the fibers were continuous. So we were trying to find the deformation of the structures using the CNT fiber. So for whatever reason, we didn't pursue the work on the fiber optics. Fiber optics are the equipment is more complex and the fibers are very expensive. I actually spent a lot of money on those fibers. We ended up not using them, but the answer is yes, we can do that. I don't think there's any other technology really. You can do through external means. You can do that, you can scan that, you can, do different type of measurements, but have an embedded sensor that can measure deformation. I don't think there is such a technology. Can it be done? The answer is probably yes. The fiber, I mean, like I said, it's a gift that keeps on giving. You can do so many different things. There's so many areas to explore and like I said, it's my passion. We do a lot of work on that, but there's really so many areas to work on. And, at one point, we need the interest of a company who's willing to, support the project and, work on that. And I think that's certainly a possibility, Lorenzo. Again, we can chat more, if you're there later in June, early July, I will be there. We can chat more about it. I think that's a great idea as well.
O Lorenzo está aqui nos Estados Unidos também, Jandro.
Ah, Lorenzo está aqui. Eu vi que tem aí o logo da NASA. Onde está, Lorenzo, agora, você?
Eu estou em Boston agora,
professor.
professor.
Tá no Boston, tá. Tá, perfeito.
Se
Não
der,
podemos falhar aí, podemos falhar. Eu estou aqui no Washington, tá? É um pouquinho ao sul aí da Boston. Eu estou aqui por 2 semanas, estou indo para uma conferência, depois volto para Brasil. Mas nós podemos. Você está trabalhando em uma companhia ali no Boston?
Não, por enquanto não. Eu vou começar meu doutorado agora em agosto na University of Colorado Boulder.
Ah, a universidade é muito boa, muito boa.
Mas se der, eu passo em Washington para visitar vocês.
Tá, perfeito. Eu estou aqui até maio 30. Eu estou saindo. Mas se você vai estudar, eu volto aqui no agosto e vou estar por aqui. Em setembro nós começamos as aulas. Aqui o ano acadêmico nos Estados Unidos o norte é distinto que Brasil e Uruguai, tá? Aqui as aulas começam a princípios de setembro, ¿no? Finales de agosto, princípios de setembro. Termina dezembro, janeiro começa de novo e termina maio. Aqui nós terminamos a semana passada, terminou ano acadêmico. Lorenzo, muito obrigado pela pergunta, é um prazer.
Eu que agradeço, professor. Eu já realmente vi vários trabalhos que eles usam, alguns trabalhos que eles usam células solares ou sensores solares para reconstruir essas estruturas. Mas o problema é que quando a gente tem essas estruturas muito flexíveis e adiciona sensores, eles acabam atrapalhando, né? Eles são mais invasivos. Se a gente pudesse ter algo dentro da estrutura para ajudar a reconstruir essas, realmente obter, né, essas deformações, seria ótimo, bem interessante.
Ah, que bom. Você está fazendo que área? Mestrado, doutorado, que área?
Eu terminei o meu mestrado. O meu mestrado foi no ITA com o professor Wheeler, na parte de modelagem de multicorpos flexíveis. Então, modelar uma estrutura de um satélite com sistemas que podiam rotacionar e também são flexíveis. E agora, quando eu for para o meu doutorado, a ideia é trabalhar em softwares de simulação para grandes estruturas, por exemplo, estações espaciais. Então, tem várias partes que podem ser móveis e flexíveis também. Então, tem esse interesse em identificar também essas deformações na estrutura.
Que bom. Você vai fazer no doutorado de engenheiro espacial na Boulder?
Isso, com o professor Schaub.
Não conheço ele.
O professor Schaub é uma das grandes autoridades, uma das maiores autoridades no mundo nessa parte de... Ô, Jandro, aquele vídeo que eu te mostrei, o trabalho que eu comentei é justamente do Lorenzo, né? Quando a gente conversou, né? O Lorenzo foi meu aluno de mestrado no ITA, e daí ele fez análise da oscilação ali dos booms, daquelas hastes, do satélite forte. Foi um trabalho muito bom.
Nós estamos falando aí com o professor Wheeler sobre isso, que monitorar a formação de um boom, usando a fibra nanotube de carbono.
Sim.
E também a parte dinâmica, porque nós podemos detectar essa vibração aí.
Isso. E, cara, a frequência de flexão e tensão ali, da oscilação de uma haste, isso também é interessante.
Eu acho que ainda não temos... nós estamos começando nesse trabalho, mas ainda não temos todos os detalhes assim, mas tenho estudante, ele completou o doutorado no ano passado. Tenho outro estudante aqui, Mohamed, que ele está começando esse trabalho. Mas nós podemos falar aí, tentar colaborar. Aí, se temos no fundo, segundo muito, não precisamos muito, uma companhia assim, se eles têm fundo assim para poder fazer um pouquinho de desenvolvimento, seria muito bom. Tiago, eu pus aí o e-mail ali, o endereço de e-mail, tá?
Muito obrigado, professor.
Eu sou muito bom com os e-mails. Eu estou sempre assim, eu vou responder a você assim imediatamente.
Muito bem.
Tá, muito obrigado, muito obrigado.
Depois dessa paciência aí, em explicar com tanto detalhe para a gente, acredito que certamente...
Sem problema. Eu adoro a fibra, até eu gosto muito da área de pesquisa. Eu sou um cara que desenvolvi todo nessa área. O sonho, my dream is to see this applied in different fields, and like Petrobras, I think it's the first company who's spending a lot of money on this, and I look forward to having more companies develop that. Maybe Embraer will be that will be a dream of mine, really.
Com certeza, tem muita aplicação, né? Dá para vislumbrar milhares de aplicações para SHM, compósito, selos aerodinâmicos. Nossa, o negócio tá bem longe aqui.
Obrigado, Thiago. Obrigado, Lorenzo, aí, pela participação também. Mais alguém? Tem mais alguma pergunta, professor Jandro? A gente fazer algum comentário? Jandro, deixa eu te fazer uma pergunta. Seria possível esse sensor medir o fluxo de um fluido através desse material? Por exemplo, eu estava pensando numa possível aplicação no bocal de um propulsor, de um satélite, para medir o fluxo do empuxo. When you have a thruster and to measure the thrust efficiency or thrust level, because you talk about the chemistry, the flow, something related to that.
So what? Okay, Wheeler. Okay, mas você tem que medir exatamente o que? Você tem que medir a pressão, ou você que quer medir exatamente o fluxo, the flux? The flux, what will be the units of that flux?
Usually, is that in the, can be the pressure?
The pressure
Or-
we can easily measure. The pressure we can easily measure. Pressure sensor, there's a lot of technologies for pressure sensors, and they are relatively cheap. All sort of, they could be capacitive pressure sensors, they could be piezoresistive pressure sensors. I mean, there are so many types, and they're very cheap. Can the CNT fiber measure pressure? Yes. If it's in the lateral direction, Iriana, I have a student, she's actually working on that. The lateral, it is super sensitive. So if the flux comes this way, okay, if the thrust comes this way, and I put the fiber this way, I can easily measure that, okay? I can also put the fiber inside the polymer and measure that pressure, because the fiber is super sensitive. So if you put too much pressure, you will break the fiber, okay? But if I put the fiber inside the material, I coat the fiber, right? So I can protect the fiber. I can measure that pressure indirectly on the fiber. Easily doable.
I see. Okay.
Now, if I can also compress the fiber, that's also a possibility. I think if you have the thrust, basically, you're talking about the fluid, basically the air, right?
I'm talking about the thrusters of spacecraft. The problem is they are so small, micro thrusters, then maybe you can put some sensor there in the output of the nozzle. Then if you have a sensor embedded in the material, maybe you can measure the thrust. Or if you have a failure, if that thrust don't emit or don't activate, then maybe you can check and see.
The fiber, okay, I'm just thinking aloud, we can speak more later, but
Yeah.
the fiber could be put in the wall of the thruster, and it can basically get that lateral pressure.
Yeah.
Now, if it's going to be subjected to the actual, flux coming from the thruster, I think we had to find a way to place it, and then it has to be a pressure that can be sustained by the fiber itself. The fiber itself is very delicate, but if you put the fiber inside some kind of a polymeric material, you can probably do that. The fiber is super sensitive. Measuring pressure, yes, easily doable.
Yeah.
Then we have to come up with a proper configuration that protects the fiber, and you can use it time and time again.
I see. Okay. No, that's interesting. Thank you.
Rafael Cruz. I think, Rafael, did you send me an email for LinkedIn? It was you? I think I got a request to, I'm not sure if it was him or not.
Oh. Obrigado, Rafael.
Like I said, if you guys, se você tem mais perguntas, assim, querem falar um pouquinho mais, eu estou chegando aí no São Paulo desde junho, tá? Então, eu vou estar trabalhando ali na ITA, eu acho que quase 3 semanas, tá? E depois vou para o Uruguai e vou voltar no julho. Tá? Se vocês querem falar um pouquinho mais, é um prazer falar com vocês e discutir ideias. Né? Estou aberto para colaboração.
Perfeito, Jandro. Então, mais ninguém tem nenhuma pergunta? Então, alguém tem mais alguma coisa para falar? Uma pergunta? Então, a gente poderia encerrar aqui por hoje. Novamente, pessoal, muito obrigado aí pela participação. Jandro, novamente, muito obrigado mesmo pela excelente apresentação que você deu para a gente, essa aula. Se quiser fazer alguma consideração final, Jandro, por favor.
No, like I said, eu vou falar em português. Um prazer estar com vocês, fazer a apresentação, e sabe, open your minds, to see what can be done with the fiber. I think the possibilities are enormous. There are so many different fields, but certainly everything takes a lot of development. First, the research, basic research. I think some of the science behind the sensors are already there. Okay, so the concepts are what can I say? The proof of concepts are already there, so they're already available. But then there's a lot of engineering and development process that has to happen, right? In order for you to be able to put this sensor in a plane or in a spacecraft or in a pipeline or in different, there's a lot of development that has to be done. I mean, the fiber is a delicate material. There are a lot of materials issues, fabrication issues, testing issues. So that has to be done. And I think that's the fun part, right? For us engineers and scientists, that's the fun part, to do that work, and eventually, there will be a product in the future that's the dream. So, like I said, prazer falar com vocês hoje, conhecer a vocês, and like I said, eu vou estar ali, nós podemos falar pouquinho mais, falar personalmente, assim, não é o mesmo. O Zoom, Google Meet, tá muito bom, né? Mas não é o mesmo que falar assim em pessoa, assim, one-to-one, né? Como decimos assim, né? Que dá para mais, assim, mais colaborações distintas, sabe? Mais profundas se uno fala assim em pessoa. Mas tudo bem, prazer estar com vocês, bom dia para todos, na sexta-feira, aqui Friday, nós temos aqui o commencement. O commencement é a cerimônia de graduação amanhã, tá? Todos os caras que completaram os programas, eles vêm com todas as famílias aqui. Assim que isso tem amanhã. Mas depois já estou preparando para viajar, fazer apresentações e estar ali com vocês no Brasil também. Eu sou paulista de coração, eu gosto muito do Brasil, mas São Paulo é muito... São José, São Paulo é muito bom.
Beleza, muito obrigado, Jandro.
Muito obrigado, Willer, pelo convite também. Muito obrigado.
Imagina. Obrigado, pessoal. Muito boa semana e bom final de semana para todos. Espero vê-los aí no nosso próximo seminário. Aí. Grande abraço.
Valeu.
Tchau, professor.
Valeu,
Tchau, tchau. Obrigado.
Valeu.
Bom dia a todos aí. Tchau, tchau.